Hello, Mm, we'll be looking at the CG7 real-time feature demo. So the agenda is we'll first look at what real-time systems are, and we'll see how do we measure the latency, and what latency is, and basically the test environment and some of the sample results. Okay, so we'll start with what real-time systems are. So non-real-time systems are basically cannot guarantee the response time in any situation, and they are basically for the high throughput or the for the best effort. Whereas when you see the real-time systems, they have operational deadlines from the event to the system response. Also, guarantee the response to external events within strict time constraints. Okay, so real-time response basically means a deterministic response, and some of the real-time examples for real-time systems are the 3G or the 4G baseband processing in base stations and network controllers, IP network controlling, and live audio video systems. Okay, so before we jump to the demo, let's see what actually this latency is. So latency is defined as the time interval between the occurrence of an event and the time when that event is handled. Okay, so some of the examples are like the time between when an interrupt occurs and the thread waiting for that interrupt is run. Also the time between an expiration and the thread waiting for the timer to be run. This can also be the time between the receipt of a network packet and when the thread waiting for that packet runs. Yeah. So basically now how do we measure this latency? We use cyclic test, which is one of the widely used tools in the industry. It measures the latency of a response to a stimulus. Okay. So what cyclic test does basically? So when an external interrupt triggers, the control is transferred to the cyclic test. Okay, so this interrupt triggering is basically the expiring of a clock, and there's a delay between the clock expiry and the transfer of control to the cyclic test, and this delay is measured as the latency. So how does the cyclic test do it? Okay, so basically cyclic test gets the current time of the day, and it does a sleep for a specified interval, and then after it has woken up, it again calculates the current time and see the difference between the earlier get time and the new get time, and this difference will give you the latency along with the scheduling time. Okay, so what is the environment we are using? Basically we use a Ivy Bridge 8 core target running at 2.2 gigs. Okay, and we'll use basically a host and guest architecture so that we can simultaneously measure the RT latencies both for CG7 running with RT kernel and CG7 running without a RT kernel. Okay, so what we do is we have a host that runs a CG7, and then we launch two guests, each of CG7 with CG7 RT kernel and the other with non-RT kernel, and we also load the target so that there is a latency. So there are few of the loads like a Hackbench load, a netperf load, and the DD load. So any of this could be used. Any combinations of this could be used. Okay, so these are the sample graphs collected on the previously set target. So if you see, this is the latencies plot for the non-RT kernel, and this is the latency plot for the RT kernel. If you observe this graphs, it clearly says that there's a huge peaks, okay, on the non-RT kernel, and if you see this scale, the scale is in thousands, and it is somewhere around 20,000 scale, and you get the maximum latency of 18,000 microseconds. And if you come back to this real-time kernel, if you see that first of all, observe the scales is in hundreds. Okay, it's the maximum is 1,000, and if you observe this, the latencies are pretty stable and operate within a range usually, and the maximum latency being 200 microsecond. Okay, so this clearly says that irrespective of the load, the RT kernel has a deterministic response which can be taken up within this band. Okay, so now let's see a live demo. Okay, so this is my host now, which is running CG7, and I have opened two terminals. So one terminal I'll run CG7 guest with CG7 with non-RT kernel, and on the other terminal I'll run uh, again the CG7 with RT kernel. So I have two terminals so that I can launch two VMs. So now let's launch the non-RT kernel. I'm using Kemu KVM, and I'm pinning it to, since we have 8 cores, I'm pinning it to core number 1 using the task set, and I'm loading the non-RT kernel on this VM. Okay, let's boot it. Okay, so the non-RT kernel is booting now. Okay, let's log in. Okay, let's confirm it's a non-RT. Okay, so basically this is disabled, which means it is a non-RT kernel. So now let's capture the log and the latencies. So what I'm doing is basically I'm running a script that invokes a cyclic test and a load, which is just doing a dd command. So, and I'm redirecting the log output to my host into this file. Okay, let's start the test. Okay, so now the test has started. So let's go back and launch the another VM with CG7 RT kernel. Okay, so again I'll run the Kemu KVM to launch another VM, and this time I'm pinning it to another CPU. So this will pin it to CPU number 2. Okay, and this time I'm using the RT images or RT kernel to boot this VM. Okay, so this is booting the RT kernel now. Okay, so let's log in and confirm this is the RT kernel. Okay, so we have this RT enabled, RT full enabled, and let's run the test simultaneously on this also. Okay, so again I'm running the same script with the same load, and this time I'm redirecting the load to this rt.log. Okay, so let's start it. So we have both the VMs now running, and the latencies are output to this log. So now we'll have this graphical visualizer where we can see the latency values. So I'll just load this first plot with non-RT log. So this gets going, and you can see the peaks. Okay, so there's somewhere around the magnitude of 12,000. So now we'll load the RT. So this is a RT log. I'll load this into the bottom viewer, and if you can see this, it is pretty stable within this region, whereas the RT kernel there's a huge fluctuation, and it goes as high as 12,000, 15,000 depending on the load. So, and if you see this is in the thousands range, and this is in the hundreds range, and it is very stable within the 200 range, and most of the times it is less than 100. So this clearly demonstrates that, okay, now we can see that there's no load on the system and it is back, and once the load is running you will again have those peaks, high latencies. But in case of RT kernel, it is always stable irrespective of the load we put, and it is very deterministic in terms of its response.